And welcome everybody to Optimization in Oslo. Today we're very happy to have Professor Johannes Royset from the Naval Postgraduate School here in person. And he's going to talk about Rockafellian functions, the most important concept in optimization that you haven't heard of. So.
Thank you very much. Thank Thomas for having me. Of course, I was trying to time this visit to the coldest and snowiest time of the year. I'm happy to succeed, I think. Good fun to be here. And what I want to share with you a little bit is kind of a little bit of general thinking about optimization. We know optimization is a general methodology to deal with a lot of different problems in applied mathematics. It comes in so many different areas. And of course, much can be said about optimization theory, algorithms, applications. In this short hour, just going to talk about a few things, maybe a few things, hopefully you do not have heard about, maybe the good directions to go and things like that. I'm going to start to think about it as kind of like a generic optimization problem. What is that? Minimizing some function phi of x. So x is my decision variables, is a big vector, and you know this is x's in Rn. So I'm going to, for the sake of this talk, stick to finite dimensional optimization problem. I realize maybe some of you, Thomas and others, might be interested in infinite dimensional problems. And I think there are some opportunities there. Many of the things I'm talking about will definitely carry over there, but to avoid too much technicalities, I'm just going to minimize in a finite dimensional space this function phi. There's one thing I'm going to do maybe that is, at least in some places, not entirely common. I'm going to think about that function phi of x as being extended real valued. With that, I mean that phi goes into not only the real line, but extended to plus and minus infinity. That means that there could be a decision that we make, an x, that has a cost of infinity. So of course, that sounds rather horrible if I'm going to be minimizing, and something I would avoid. So that would be a way I can represent a constraint, something that is not allowed to do by having an infinity. But we want to see a much more concrete example as we go along. So if I have such an optimization problem, of course, there are a lot of things we would like to deal with. We would like to do, for instance, a bit of an analysis of the problem. Is it well posed? Does it have solutions, or all these things that we typically deal with in applied mathematics? It could be sensitivity analysis. And these are all important things that it turns out that this concept that I call Rockafellians are going to play a role, are going to be helpful in one way or another. Optimality conditions is also something that's very important in optimization. It's basically a way to say, hey, I have an optimization problem, I want to find the best x, but that might be a bit hard. So what we can do, we can write out some conditions, think about equations that might be able to more easily solve, that can serve as some sort of a surrogate for this optimization problem. And we like to examine such conditions. Again, these Rockafellian functions are going to come in as very handy there. An important topic in optimization is duality. It turns out that we can associate various optimization problems with some other optimization problems, maybe that are more tractable or nice in some way, but they're also equivalent to the original one. So that's another place where Rockafellian is going to play a role. And of course, all of us are interested in algorithms of computation. How can you actually find a good X there? And it turns out this Rockafellian function, again, going to play a role. So wherever you go, there's going to be some role for these Rockafellians. Okay, so what are these Rockafellian functions, or just Rockafellians in general? So I already told you this is the problem I'm interested in. And just to remind you again, this R with a bar top, that means I've extended the real line to plus or minus infinity to just handle this special case with constraint, for instance. Okay, so here's a definition. If you want to take one definition with you from this talk, this is one. What is a Rockafellian? It's a bivariate function. So it's a function dependent on two arguments. Remember, my phi depends on x, but now I have a bivariate function depends on x and something else. I'm going to call it a u. So it depends on u and x. And such a function, a bivariate function, is a Rockafellian if I can come up with some u bar, so some particular u, if I plug that into my function f, I reproduce my objective function pointwise for every x. So if I pick just that lucky U, I reproduce my objective function of the problem that I'm really interested in that's on the table. Of course, there are other U's as well. But if there's one, I have somehow represented my actual problem through this F. Okay, so that's the Rockafellian. It's pretty general. We could do, and by the way, that special U is what I call the anchor U bar. Okay, so why do I call it Rockafellian? Well, some of you might know Professor Terry Rockefeller. This is a concept that goes back to Harvard University in 1963 when Professor Rockefeller graduated. A PhD in mathematics, and one of the things that he has a dissertation is the precursor to this. If some of you have seen, there's a very famous book on convex analysis called Convex Analysis. In fact, that was where the term was coined out by Rockefeller in 1970. And there, this concept that we now call a Rockafellian is called a bifunction or the bifunction. We thought that was not necessarily the best name. Rockefeller himself didn't call it Rockafellian, but we have, in our recent book, decided to put that name out there and see if it picks up. It hasn't gone viral yet, but we'll see. Okay, so just to summarize a little bit, we had a real problem, some phi, that gave us what I call the actual problem. So think about that came from your application. Whatever you're interested in, to optimize something, this is what we have on the table. And to recap a little bit, somebody comes up with a Rockafellian. We're looking for suggestions. Here's a Rockafellian, maybe it's Rockafellian F. What does it gives us? It gives us a family of problems because the Rockafellian depends on this additional degree of freedom, these U's. So as I change U, for each U, I have an optimization problem. I have a whole family of problems. And of course, there's one special one. If I stick in a particular anchor U bar, I get back to actual problem. But there's all these other ones. Okay. So really, long and short of all of this is that Rockafellian defines a parameter of parametric family of problems. One of which is the original one, the actual one that we're interested in. So what can that really get us in these things we want to talk about? But maybe first we can talk about some more concrete examples, some concrete formulas. One important problem in stochastic optimization and machine learning and these type of areas is this problem. Imagine that my phi that I've been talking a little bit about has a particular form. And there might be some F naught, maybe that's some sort of regularizer or something, who knows what that is. But then there's a sum over I over S things. Think about that, maybe S scenarios. So maybe these are probabilities. This piece of probabilities assigned to different examples, different scenarios that might come our way. So if you want to do machine learning, your problem is probably of this form, where a neural network might be hidden inside Fi and things like that. So this will be a particular type of problem you might see. And here's the challenge in that area, is that this probability Pi that I'm assigning to different examples, different scenarios, might not be fully well known. Who knows where they came from? Maybe I even have data that shouldn't be there and things like that in my optimization model. So we're interested in what happens if there's contamination, if there's outliers, if there's even an adversary that comes and messes with us. That can be interpreted as changes to that P. So this P is really just a nominal value, but there might be changes to it that we would like to account for as we optimize. What type of Rockafellian should we cook up in this setting? Well, here's one proposal. But all of you can come up with your own Rockafellian. This is a free country. We can do whatever we want. So you can come up with your own Rockafellian. But here's my choice, for instance, as a possibility. I say a Rockafellian depends on two things, U and X, right? So we have to say, how does U enter? Well, here I let U enter here as a change to these probabilities. But that's going to be a little bit of a guiding principle for me, is that if I'm a little bit worried about what these probabilities are, I'm going to put in U somewhere connected with that. Because I'm going to use this U to kind of examine the effect of changes to probabilities. So I can see that here, as I change U, away from the nominal one, u equal to 0. So that becomes the anchor here. U equal to 0 is the anchor here. But what happens if something else? So I get a whole parametric family of problems from this Rockafellian. Okay, so you might wonder, is it really a big deal if I change these probabilities, or for that matter, any other thing in my optimization problem? Well, what is the fundamental thing we often are worried about in mathematics is sensitivity. If I have a model, it depends on some parameters, but the parameters are somewhat unsettled. If I change those parameters a little bit, will the solution of being your OD, PD, or optimization problem, will I change a lot if I change that parameter a little bit? That would be worrisome because I will have some sort of instability. So in my case, I might be concerned about some optimization problem here, and there's expectation here. Expectation is taken with probability measure P. But as we talked about, P could be a little bit unsettled. So can a small change to that probability measure be dramatic? Okay, that would be bad news. So let's look at a very simple example. Here, I'm taking the expectation of this integrand is G. And what is that G? Well, it's a very simple formula. And the probability measure P is given here. And this is, maybe world record in terms of simple probability measure, because I put all the probability mass at 0. So of course, there's nothing uncertain here. But this is my simple probability measure for all the probability masses. Okay, so I can probably figure out what is the minimum value here, the minimizer, in fact, x equal to 1. I worked hard on that. I figured that out. So, but now let's see if we twist the story a little bit. Imagine I change that probability measure P, which by the way has, of course, that step function as a cumulative distribution function. If I change that P to with a little superscript nu, what I indicate this is just a P nu, some sort of approximation. That is that red cumulative distribution function. Of course, that red is pretty close to the black. In fact, you see the jump here happens at nu. So as nu goes to infinity, this actual red converges in some sense, in fact, converges in distribution to the red one as nu goes to infinity. So it seems like the red is pretty close to the black, no doubt about it, in particular as nu becomes large. But if I replace that probability P with the red one, what happens to the minimizers? Well, and here is the bad news. Now the minimizer becomes 0. Used to be 1, but now it becomes 0. And that is regardless how close that red line is to the black. So nu can go to infinity, but the solution sits at x equal to 0. I don't have any convergence. So even this tiny change in the probability measure has a dramatic effect on the change of solution of this optimization problem. So this is really worrisome that it seems like even in this rather, simple problem, I can have this type of instability. So I'm particularly interested in machine learning, statistical learning. These type of changes in probability distribution that we just talked often comes in terms of, for instance, that have a data set for statistical training, but that data set is somewhat corrupted or there's mislabeling and going on. So really, I can interpret that as has incorrect probabilities assigned. Maybe that probability, maybe like 1 over n, each example is given 1 over n probability. Now that should even be, that probability should be 0, really. It should not 1 over n, but should be 0. So in such situations, I wonder, we seem to have this instability fundamentally that we saw in the previous slide. And the question is, can we do better using this Rockafellian? And maybe a little bit of preview. We see if we have time, we can return to. If I do classical, what we call empirical risk minimization, is basically saying, let's ignore what we just have been talking about, this instability. If we ignore that, often we might have the following situation, that if you look at this orange line, that is really what we are looking for, is in the test accuracy. How accurate is your statistical model? And it looks like as I keep optimizing, and on the first axis, we have how much optimization I'm doing. And you see that actually things are getting worse. And that's something that we would like to avoid. But we cannot, on the blue line, that's what we see when we're actually optimizing, how things seemingly get better. But if we test it and see how it actually is, it is getting worse. How can we do that? Well, we are thinking about how using this Rockafellian in this case. So this is a bit of a preview. But you see, you have this kind of general trend that eventually things go down. But what you see from these two curves is that they are very much in tune compared to here. They go in the opposite direction. These are very much in tune. So when I'm optimizing and see this is going up, I can see when I'm on the top and start going downhill. And then I can stop. And when I stop there, I'm actually on the top of that one. And I want to get the top here, which I couldn't have identified over there as easily. Well, at least I have to stand on my head more. So I work with some people at Facebook on this in the context of hate speech and computer vision, things that we think Rockafellian can play a role in that area. Okay, maybe we can skip that. Let's see what we want to talk about a little bit more systematic. I mentioned optimality conditions, sensitivity analysis, dual problems, and all of these areas are things where we think the Rockafellians can play a role, and try to give you a little bit details, and then we'll run out of time, we'll see how far we got. So let's start with optimality conditions. So remember, my goal is to minimize 5. Yeah, so this is my problem. So what is you learned, the Norwegian schooling system, I know at one point or another, wherever you went to school, you learned about taking the derivatives that equal to 0. Okay, so that is the most fundamental optimality conditions we have in optimization, is take the derivatives that equal to 0. So of course, multivariate setting will be gradient should be equal to 0, but that's fine. Okay, so this is all good. That will be the most basic optimality condition. So when I talk about optimality condition, think about gradient equal to 0. But that is if I have a continuously differentiable function. Of course, that might not always be the case. So what can we do if I have an arbitrary phi that is not necessarily smooth? Well, then we can use sub-differentials. So I'm going to talk a little bit about how one can define this curly thing for general function. It turns out that for any function, we can define optimality conditions like this, which basically says that there must be a subgradient of that is the 0 vector. Okay. So that is in a way good news. But so what is this phi? Well, if I look at a rather crazy function, here I drew a function phi. And this function phi is a little exotic in the sense that, well, it's nice and smooth, but then there's a place where it's vertical. Okay. And then there's a place where it's a kink. Okay, so that's already throws out of this differentiable setting. And then here's even worse here. Here's a place where the function jumps to plus infinity. Okay, so over here, the function is always plus infinity. So, of course, the usual calculus that we learn at one point or another, that will not fly here, everywhere at least. Here I will, there's a smooth point. Of course, there, that curly thing, which I call the set of subgradients, is just a gradient. Okay, so these subgradients, in this case of smoothness, it's just a gradient, so nothing new. What happens when I get down to a kink? Well, the set of subgradients here are actually, think about all the slopes that you have here. So there's a whole set of slopes. Well, it has a unique slope, but it's a set of slopes, and all those slopes are called subgradients. And for that to be a minimizer, I need to make sure that there's a 0 slope in there. And is there a 0 slope in here? Yes, it looks like there's a 0 slope here. So that is indeed a point that satisfies this optimality condition. Okay, here's a kink, but it's an inward kink. It's an inward kink. So there is a little bit tricky, but as I defined it, in what we call in the general sense, you have 2 slopes only. And certainly none of them are 0, so that doesn't satisfy optimality condition. So it shouldn't, because obviously this is not a minimizer. And here's a tricky place where it choose the infinity, but it's really nothing new for us, because we're still going to look at all the different slopes we have here. And indeed, of course, the slopes can get steep, steep, steep. So in fact, the slopes are, I eyeball it from 1.2 up to infinity. Okay, but these are the set of slopes there, the set of subgradient. But regardless of what it is, what I'm trying to convey to you for an arbitrary function, forget about smoothness, okay? Don't need it. For arbitrary functions, phi, we can define optimality conditions like this. Okay. So this is all good. And we talk about, for instance, in our book, how one could do all types of calculation rules regarding these type of subgradients. You can do, you know your chain rules for usual derivatives, and you do that for the non-smooth case as well. Okay, where's the Rockafellian coming in here? The Rockafellian comes in the following way. Imagine that I have talked about that many times now, minimize on phi. Okay. And then I go around the table and look for a Rockafellian. Somebody needs to propose a Rockafellian for me, and here it is, F. This is a Rockafellian. I'm going to just assume that there's a proper lower subcontinuous Rockafellian, so it's not much of an assumption. And I'm going to assume there's some sort of anchor. We saw an example where anchor was 0, who knows what it is. But what's important to me here is that I can use this Rockafellian to find optimality condition that might be simpler than what we saw on the previous slide. It turns out, at least under a small qualification, that if X star is a local minimizer of the problem, meaning the problem minimizing phi, then the following thing is an optimality condition. There's always going to be a Y such that Y and 0 is a subgradient of the Rockafellian. So here's one takeaway is that every Rockafellian, and you can have your own if you want, every Rockafellian will get you an optimality condition. Okay. Get your own optimality condition. That somehow you might pick one Rockafellian that produces an optimality condition that's almost computation tractable or convenient. Okay. And you might have heard about things like Karush-Kuhn-Tucker conditions or something, KKT condition. That would be a special case when you select a particular Rockafellian associated with a particular type of problem, you will get from this Rockafellian, the KKT conditions. So some of that, I guess, might come out from this. Let's try to get a little bit more concrete. I imagine that I put my problem consisting of all these different pieces. So let's look at it. So imagine that my X is of a rather particular form. What does it consist of? Well, let me maybe start in the back. There's an f of x. Well, that is maybe some quantities that we are worried about, vector valued, and it sticks into another function f. So some sort of composition. And then there's some term here, it's another function. And what is this stuff there in the front? This I there looks like actually the Greek iota. That's going to be my indicator function. I guess I define it down here, that if x is in the set capital X, it's going to be 0, just simply 0. Otherwise, it's going to be plus infinity. So this is a way for me to maybe capture an abstract constraint set or something. But I'm trying to just give you like some sort of formulation that might be a particular type of form of phi. Okay, so suppose this is the problem that sort of ended up my table. One particular kind of this could be just what you see in classical optimization, even like linear programming, convex optimization will fit in here, a special case. Maybe you have some concrete examples. For instance, we looked at this a little bit earlier today, where it was an F naught. I guess we saw an F naught on the previous slide. We saw an H. Well, I guess if I think about that sum and pi as my H, as you see there, this will indeed fit into the form that you have on this previous slide. Optimization with the objective function and some equality constraint that will also fit into the form on the previous slide, and the other version as well. So there's many cases here. So now what can we say in terms of optimality conditions? Well, as usual, we need to have some sort of assumption. Maybe X is a closed set, these F's are smooth, and this H might be a proper lower sum continuous convex. Okay, so maybe this is what we have. I would like to have an optimality condition. Here we're a little bit of trouble, of course, if you want to fall back on calculus alone. Calculus alone said take the derivative, set it equal to 0. But I can't take the derivative. These are non-smooth things, right? Because this was an indicator function, shoots from something to infinity. This H might be a non-smooth. So this is a non-smooth problem. This is not necessarily convex. So a lot of the trouble that we would like to deal with is hidden inside this problem. So how can we get a meaningful optimality condition here? Well, we work to a Rockafellian. So we're looking for, somebody come up with a Rockafellian. And here's indeed a Rockafellian that goes back to Rockefeller. And this is where the U, always when I say come up with Rockafellian, just means where should U enter? And here it enters in the back here. So this is now certainly a bivariate function U and X. Okay, so remember from the earlier slide, every Rockafellian will give you an optimality condition. What was it? Well, I guess it was the first line here. Optimality condition was this Y, and 0 must be a subgradient of the Rockafellian. But the question is, what is a subgradient Rockafellian? And that is where we need to open some book, for instance, a book we wrote recently, and try to calculate that set of subgradients. Same as where you have chain rules for computing derivatives, we have chain rules for computing the subgradients. Start working those rules, and I can show you that these are the conditions that come out. So this becomes an optimality condition for this particular problem that is a little bit more concrete in the quantities that you have available. Okay, and I think there's a special case, say if you have equality constraints, justice and objective function, but equality constraints, actually that goes back to Lagrange. So this is basically what Lagrange did, and this, if fits in here, and you might recognize this as the Lagrangian possibly, where the Y are the Lagrange multipliers. Okay, so that comes out as a special case. So that was a very quick tour about optimality conditions. What about sensitivity analysis? Okay, so can Rockafellians play a role there? So let's see what type of result we can obtain. So again, somebody needs to propose a Rockafellian F, okay? I said some mild boundedness or something, we can talk about that later. We're going to get something, but let's define notation. I talk about this mu of U. Well, maybe it's easy to look at what's here on the right-hand side. Remember, this is a Rockafellian, and what happens if I plug in the particular U bar there? Then I get back to the original problem, the objective function. And this infimum here, I just say, let's minimize it. Okay, let's minimize this thing in X. So if I put the U equal to U bar here, I'm just saying, let's do the original problem. But if I change U, I'm talking about other problems. So what this is doing is just looking at the minimum value as I change U. Now, obviously, as I change U a little bit, the minimum will change. And what we're worried about in sensitivity analysis is how much does this minimum value change? Obviously, this talked about earlier that if I have an optimization problem, there's a parameter U. I might not know exactly what it is. And if I'm very, very sensitive to small changes there, that would be a little bit tough to go and talk to people about, because you have some fundamental instability in your model. So we wonder, is that mu function of U somehow varying gradually, continuous, for instance, and things like that? So how can we discuss that? In particular, how can we quantify the changes in this mu as U changes? So what you might think about is to compute the gradient. Let's compute the gradient of this mu respect to U, and then get to kind of how much things are changing. But again, this is a non-smooth setting, so we have all these kinks. But I said, don't worry about that, because we can always compute subgradients. So this curly guy comes in again, so we can compute the subgradients. So now the question is, how much are these subgradients? How can we compute them? It turns out, and here is the result, which by the way, goes back to Rockefeller, so don't give me any credit. The following is that if I can compute the subgradients of this Rockafellian and look at those Y's that I compare together with U or subgradient, those Y's are the subgradients, at least an outer bound of those subgradients of the minimum value function. So if I can just look at my Rockafellian and the subgradients, I get a sensitivity analysis directly from it. Okay. Yes, directly sensitivity analysis from our Rockafellian. I can do that in this composite setting. Remember, we looked at all these pieces before. Of course, I can go through the same exercise as before and get specific formula for that case. I work for the Navy, so at least I need to show you one picture of a ship. Otherwise, they will not take me back. And here's one ship. So basically, you see this big cylinder there. This is like a Tomahawk missile or think something like that. They are fired out of these tubes. Okay, so in the front deck of this destroyer, there's all these tubes where they hoist in these missiles, and if somebody pushes the button, a missile comes out. So this is the situation. But here's the problem for our Navy planner is that what missile should I load? There are missiles for shooting at other ships, the missiles shooting at land, there's missiles shooting at planes, and who knows? I think the US Navy has something like 20 different missiles that they can consider loading on board. So how much? See, there's a finite number of loading possibilities here. So what should you, in particular, this is once the ships travel together, so how should they together have what they need in case of a future situation? Of course, a future situation is not settled. We don't know what type of mission they will be called upon while at sea. So I would like to do some sort of sensitivity analysis on what is the effect of making some, how well will I do as I change my demand, the requirement that I need to respond to. So let's look at that a little bit. So what is the best combination of missiles to have on board on a bunch of destroyers? And what is the cost of a decision that is robust to unsettled requirement? Because really, I would like to load on board something that can handle many situations, that is robust for, if, who knows, war here, war there, or whatever it might be. I would like to have a decision that's robust to these possibilities. But of course, if I try to be robust, maybe that would cost me something. Like always, a kind of buying robustness will cost me. How much does it cost me to do that? So I'm just going to show you some numerical results for this particular situation. And remember, what was this mu? We talked about that. That was the minimum value of an optimization problem as we saw it earlier. And what does it depend on U? That was something that was unsettled. We looked at sensitivity to these changes to the U. And in this particular, turns out that there's a big optimization model that's underpinning all of this that I can abstractly write like this, where I'm going to make a decision X. That's like basically how much to load on board. And a few other things, because to load something on board, I might like offload something because there already was something on board and things like that. So these are the decisions I have to make. And what is this A that is in a set? Well, that is how much robustness I would like to build in. So think about A is sometimes how many missiles I will kind of need, but I don't know how much I will need. I look at the worst case in some sort of set. But how big should I set the worst cases be? Well, that depends on the U. So I'm really asking myself, as I'm changing how robust I am, how much does this minimum value change? And I just to show you some numerical results, and these are 4 cases. I'm looking at different type of change. What does that mean? That means there's a certain penalties that I get from having to unload the ship and load it again. So think about this, the different parameter settings that we'll have in these type of models. There's some cases of different cycle constraints. What does it mean? Well, these ships only go out on one trip, but they come back. But if they come back, are they going to have the same thing that they have on the first trip and things like that? Are there various constraints related to having multiple cycles at sea? But regardless of what that is, there's 4 cases. And what we're doing is we are going to look at the minimum value if U equal to 0 and compare it with the minimum value where U is something else. So we will hope to try to predict this value by doing, the good old, I guess, like a derivative prediction. You know what the function value is here, and we're going to do the derivative to figure out what is going to be over there. So I'm going to take what's here and take a subgradient to see what's over there. And if I do that type of prediction using the formula from the previous slide, I get like 11,000, but the real thing is 9,000. 10,000, the real thing is 9,000, 4,000. So basically, the discrepancy with these 2 numbers is basically what you think about if you have a smooth function, a gradient projection, how much is the little gap there. And you see that it's a little bit of gap, but it's not too bad. The takeaway from this is that even using these subgradients, I can make a prediction that you could have done with usual calculus. Okay, so even if it's non-smooth, I can do this type of calculus.
I mean, 24% is pretty bad, though.
Hurt my feelings. I guess so. So that was a case where there's a little bit tough.
Lack of stability, or
yeah. So you know, you're higher bars than me, you know, higher quality tolerance. But yeah, maybe that's the case that was a little bit tricky. So we can say, hey, there we need to go back and look more. I mean, say we're not sure. This looks like a little high. Maybe I can live with that. Okay. But of course, these are integer programs. Okay. There's nothing continuous here, so things can change wildly.
Right.
So it is. I don't know. I don't have high standards. I mean, I thought it was pretty okay. But I understand your point. Maybe the admiral will agree with it. Okay, so we talked a little bit sensitivity analysis, and let's talk a little bit about the relaxation dual problem. So we have this actual problem, no doubt about that. And let's now for a moment, and maybe even for the remainder of the talk about where the anchor is 0. It turns out that when somebody comes up with a Rockafellian, you will automatically also have proposed a relaxation of the original problem. What do I mean with that? That means that if I, instead of solving this actual problem, if I solve this, what we call the Rockafellian relaxation problem, which is to minimize the Rockafellian minus a linear term. If I do that, that involves both U and X. That is a relaxation, meaning that if I do this, I'm going to get something that is just as low as that or lower, because I have more wiggle room. So this is a relaxation that can be used to get a lower bound. That's really something that's important optimization to get a lower bound. So every Rockafellian, you can propose whatever you want. Every Rockafellian will give you this relaxation of the problem. And maybe you're clever and propose a Rockafellian such that this problem is much easier to solve than the original one. Okay. So that might be a strategy that you might pursue. And the thing is, this minimization here that I saw you on the previous slide involved a y. If I now try to tune that y to find the best one, keep in mind for a fixed y, I got a lower bound on what I'm really looking at. But if I fiddle with that y, I can take the y that gets me as high up as possible. So that lower bound is as tight as possible. So I might be interested in maximizing over y, that minimum. And that gives me the tightest lower bound in this setting. And that is what we call a dual problem. It's the fiddling of y. That's the dual problem. Okay. And, you know, as we, you know, alluded to, that's always going to be below the minimum of the actual. And sometimes it might be even equal. In linear programming, convex duality with a constraint qualification will be equality. Okay, where's Lagrange in all this? I've talked about Rockafellians, but you know, poor Lagrange has to have a say as well. It turns out that every Rockafellian F, if I carry that minimization just in U, I'm going to get something that I call a Lagrangian. Of course, Lagrange himself didn't look at it in this generality. He looked at it in the special case where the Rockafellian was a rather particular one in the case of equalities, smooth equalities, and he defined the Lagrangian. I said, but we can think about generalized Lagrangian in this sense. So again, another takeaway, if you come up with your own Rockafellian, you will have produced your own Lagrangian. And if you want to have your own name in front of Lagrangian, if you want to take credit. So let's look at a concrete example. Imagine I'm going to fly an unmanned aerial vehicle of some kind. I'm starting down there. This is a terrain map, and I'm going to get up here. But you can imagine I want to get up here at the shortest amount of time. Okay, so that would be actually can be formed, at least if I discretize this space as just what we call a plane shortest path problem. And that can be solved very, very quickly, so that's all good. But what if I spice it up a little bit and add some additional consideration? Imagine somebody shooting at you while you're flying up there. And this is something you're familiar with. For instance, if there's a guy sitting here with the range indicated by the red circle that shoots at me, and here's another circle. It's a very big circle. It's the big red circle here. And this guy has a very good range. So he's also shooting at me. But of course, this is 3D. I don't see that in this image, but there's terrain here. This is somewhere like in Norway, ups and downs. So you can find the values. And so you may be actually hidden from this guy sitting there. But whatever the circumstances, I have two considerations. I want to get up there quickly, and I don't want to be shut down. So now it's not a constraint shortest path. sorry, it's not a shortest path, but it's a constrained shortest path, where I want to minimize time subject to low risk or low chance of being shut down. So that becomes a little bit harder problem. How can we formulate this? And it turns out, again, Rockafellian will come in as handy. Because what we can do, we can formulate this problem as minimize something. Maybe this is the time part. X is like, your path. And then I said there was some constraint. I can use this iota function to capture here. I can even capture Q constraints. I said just there was one shooting down constraint, but imagine there could be many other fuel or something that who knows how many constraints there are. It might be Q constraint. So we have constraints. So that is causing me trouble. It's not the shortest path anymore. But what I can do, I can propose a Rockafellian. And here's my Rockafellian, and I introduced a U in the back here. This is my Rockafellian. That Rockafellian gives us a Lagrangian according to the recipe we talked about from the previous slide. And the nice thing about this Lagrangian is that it somehow got rid of this constraint that comes up in the objective function somehow. So I can now minimize this, and that is just the shortest path problem. So to minimize this Lagrangian turns out to be much, much simpler than minimizing the actual problem, which had this fundamentally difficult constraint. So this is an example where I was clever. We introduced a smart Rockafellian that gave us a simple Rockafellian relaxation, a simple Lagrangian that can be solved more easily. So that is one way one can handle these things. Okay, let's talk a little bit at the end now about stochastic optimization with distributional ambiguity. So we have seen some of this before. Imagine that we have a situation, there's some F naught, and there's these S scenarios. Maybe you want to think about these S scenarios having probabilities pi, each of them. And one thing that worried us earlier was that these probabilities might not entirely be settled. Maybe your colleague guesstimate somehow these probabilities. So we need to do a little bit of sensitivity analysis. What happens if this probability is changing? Maybe even some of these probabilities are supposed to be zero. That is a scenario that actually we are not supposed to consider, but we are currently, and that could be a concern. So what is the effect of changing this P to a P nu? This is something we talked about in the early part of this talk, right? That a small change of probabilities can have this dramatic effect on solutions. So certainly we want to avoid that. So how can Rockafellians help? Well, I kind of point a little bit in this direction earlier that we can introduce a Rockafellian with this, the U shows up here as changes to the probability, because that's what we're worried about, that we're putting the U there. And so this is the Rockafellian, but in this case, I'm going to try to do something a little bit funny. I'm going to say, in addition to put the U here, I'm going to put the U here. This is the indicator function for the set 0. What does that mean? If U is equal to 0, this is 0. But if U is not 0, this is infinity. So that means that I'm basically telling myself, wherever you step outside 0, I'm going to have infinity. So while this is indeed a Rockafellian perfectly fine one according to the definition, it is one that is a little bit silly in the way that having additional flexibility of changing U is just kind of notional, because really, I want to step outside, I'm kind of blown to infinity. So that's all good. So let's say I run with it. And let's now introduce the fact that it was motivation initially that P is replaced by P nu. So this P, I don't really know. So let's say what happens if I change this? So replace that P by P nu. So that's what I do here. And that's why that Rockafellian F, see I call it F nu now. That's because this approximating P is come in. But then I'm going to do another thing here. This indicator function, of course, I can't compute with something as 0 infinity or something else. I'm going to approximate that the same way as P has been approximated. I'm going to approximate it. I'm going to approximate just like a 2 norm. So, 0 and shoot to infinity, that kind of gets approximated by U, right? Or something like that. So that sounds like this can be a fair approximation, where theta is the parameter they're going to go to infinity. And then you notice that when I have P plus U, this thing might not even be a probability. It could potentially be negative, so I don't want to deal with that. So I'm going to put in a constraint that says that P nu plus U is always going to be a probability. So that delta is just a probability simplex. non-negative values summing to 1. Okay, so whatever it is, this is my situations. And here's a question on the table. You remember the Rockafellian relaxation business? That was, instead of doing the actual, let's optimize over not only X, but X and U. Okay, it was a relaxation in general. And now we have a little bit of a complication because, of course, we approximate this, but whatever it is, we have a situation where we wonder, is it a good idea to solve this problem in lieu of the actual one? Well, we can't really solve the actual one because the probabilities are unsettled. And you might wonder, could we just simply switch these P by P nu? That could be a possibility. But that was a thing that we ruled out in the very beginning of this talk. Just switching in the probabilities is not a good idea because we don't have the stability. So the question is, doing this instead, which uses the probability P nu that we do have, is this somewhat fundamentally more stable? Is this problem that looks so different than the one up here? Actually, this is much closer than you might think. So if I solve this problem, I'm going to get something that's close to what's up here. And the answer is yes, if, on the following assumption, just lower semi-continuity. I don't need any smoothness, convexity, any of these other properties, just a lower semi-continuous function. I need a theta go to infinity, and it has to go with a rate that relates to how fast P nu goes to P. But now, if I now solve this approximately problem that you saw on the bottom, and produces some U's, and produces X, and if they converge to something, what is that something that I'm converging to? And here's the good news of the day. That X converges to an X that minimizes the actual problem. So I actually converge to what I want. And this is dramatically different what we did in the earlier. Remember, we had a solution that was 0. And then regardless how accurate I become, the other solution was 1 or was vice versa. But here, indeed, I do have a convergence. And actually, I can even do better. I can figure out the rate of convergence. The rate of convergence is this eta, which is 2/3 the rate by which P nu goes to P. 2/3 anyway, is a little bit of interesting numbers. So we can talk about that. But we have that rate of convergence as well. Again, dramatically different. We didn't even have a convergence if we do this naively. Okay, so maybe I'll summarize this and then I kind of wrap it up. So you might wonder, what am I really doing? It's simply somewhat of a favorable thing to do, to minimize in both U and X instead of just X. I minimize both U and X. What is that really? I can work on that formula. In particular, I can try to minimize U first. And what do I get? That if I minimize U first, I can actually show this formula here, that this thing is the same as that. And what is this? This looks remarkable thing. What we start out is that P is replaced by P and U. So in fact, if you ignore the red part here, this is what I told you not to do, to simply plug in P by P and U. This is what went astray in the very beginning of this talk. But we're not doing that because we had the red term in the back. So think about that red term as a regularizer. So what this is doing implicitly, introducing a regularizer to a problem that gives us this stability that we want. But it's not a regularizer that you must see in statistics, because in statistics, regularizer is plus something non-negative. This R function is actually non-negative, but this is minus something non-negative. So this is like a deregularizer. And by the way, it shouldn't come as a big surprise because I'm relaxing. So I need to go further down. There's something below there that I'm doing. And that can be quantified as R. By the way, what is R function? There's a formula for the R function. We do the convex duality to kind of work out what is R function, which is actually a smooth function if these F's are smooth, but whatever the situation is. I think I'm running a little bit out of time. So
about 5 minutes.
Time is okay, good. So maybe I can tell you a story about some outliers. So imagine that you want to figure out a computer vision algorithm that can classify handwritten letters and things, handwritten letters here. So the M in this data set has handwritten numbers, actually. So we want to identify handwritten numbers. So that's, I guess, is old problem in computer vision. So it's not a big deal, but let's try to spice it up and corrupt our data set. So instead of having just a training data set of handwritten numbers. Let's put in some letters. So I'm going to have 60,000 MNIST, which are numbers. And then I'm going to have 600 carried from the characters data, which are letters. So I'm corrupting the 60,000 numbers by 600 letters. So in a way, in the thinking that we'll be going through now, we now might assign every image here, the 60,600 images, we might give them equal probability. And that's what one would do in plain vanilla statistical learning, give each image each same probability, 1 over 60,600. So that might be the nominal probability that we might think we should use. This is the number, but it's incorrect because the true probability we're supposed to use is to give those numbers, the MNIST from the MNIST data set, that probability. And those letters that got snuck in there, they should actually have probability 0 because they're supposed to be there. I'm going to train computer vision recognizing numbers, so I don't want to have letters in this case. So those probabilities should be 0. So in fact, here's a situation, a concrete example, where you see what was the source of having the wrong probabilities is the data had some sort of corruption. Okay, so what I've been saying that don't do this was to say, let's just plug in these incorrect probabilities, these ones, and run with it because it doesn't have the stability that we like. So we don't do that, of course. We have listened to my talk and we say we're doing this instead. So this is the Rockafellian business. I come up with a Rockafellian, P plus U, you've seen this before. In fact, here I changed it. I skipped a couple of slides. Here I changed it. I just want to give you another Rockafellian where there's the 1 norm. Used to be 2 norm a moment ago. But of course, you know, you can put a norm you want, you could imagine you get your own Rockafellian. So there's a 1 norm here. So that is the one we use. We use the 2 norm too, but it's a 1 norm I'm going to use in this particular case. So I'm going to optimize over U and X. So you will say, how can I do that? Well, there might be some theory that I'm going to develop here, but we're doing a alternating direction heuristic, meaning let's first fix X, optimize over U, fix U, optimize over X, go back and forth. And the optimization over U here is just a linear program, actually. So it's very easy to do. And for a fixed U, optimizing X, because now this FI actually is a neural network and the usual things. So to do that, we have to do something like a stochastic gradient descent of a lot of packages, PyTorch, etc., that can do that for us. And what do we get? Here's a picture about after running this, what are the U's that came out? And remember, if we look at those 600 data points, 600 images, they're not supposed to be in this data set. What are the U's associated with those? 544 of those U's out of the 600, they got a value of negative 1.66 10 to minus 5. And you might remember that number, 1.6, that was the number that I gave nominal to all the probabilities. So when I have a U that negative that means that that U cancel out that P. So that example, that image got 0 probability, which was supposed to have, it was supposed to be there. So 544 got knocked out of the data set, adaptively, part of the algorithm. We missed some. What is it, 36? No, 56? 56 were missed. So they remained, but apparently it didn't throw us off too much. But we kind of clean up the data set in this adaptive fashion using this Rockafellian. And I can talk about mislabeling, early stopping. I alluded to that a little bit earlier.
Yeah, go for it.
You want to talk about it? You like early stopping? Okay. So this is a little bit of a tricky case. Again, this is in computer vision, but it's a computer vision with label errors. And this is a common problem. We have a training data set, but incorrectly labeled. I'm just doing handwritten numbers 0, 1, and 2 here, and 50% of those labels. So I might have an image of 0, but I label as 1. And I'm giving this that for the training. And 50% of my data is messed up in this fashion. This is not good news, in particular if you do the plain vanilla empirical risk minimization. That's what you have to do, PyTorch, TensorFlow, and all those things. You will get this picture here. What does it say? The blue line is the accuracy as I optimize on the training data set. I keep on optimizing, and seemingly things are getting better and better accuracy. But this is just an illusion. Because if I bring in a test data set, actually things are going south. So I'm really over-optimizing. And I might not know that even if I try to do a validation test or something like that. But if I do Rockafellian, I'm calling Rockafellian risk minimization just as in analogy to the empirical risk minimization. So this is the Rockafellian business that we'll be talking about. We have this in coordination, these are very much in tune. So if I'm optimizing, this is what I'm seeing from my algorithm. I should stop. And say, oh, this went south, so I know when to stop. And if I stop, that's when the testing is on top too. So I can I have a way of determining when to stop. And this early stopping process is something that people really do. And what they often have to do in practice, you need to have like a third data, so what we call a validation data. They often reserve 20% of your training data for the validation. Choose up valuable data for just doing this additional testing. And even that is a little bit unreliable. So we think even Rockafellian can have, this we have no theory for, but we think even the Rockafellian can help us with this early stopping. We can see far is, recognizing cats and dogs and things like that. The same story there. This is the work with Facebook people. And this is toxic comments. Of course, you guys are very well behaved. Don't never write anything angry on Facebook, but some people do. Fortunately, not too many. So this is a data set where 3% of the posts are toxic, whatever we want to. The problem with toxic comments is that who's going to label them as toxic and not toxic? So many of these labels are incorrect. They're sent to some country where people are sitting and labeling these posts and may or may not pick up if this is toxic or not. So this is a situation where, first of all, we have a small percentage of toxic comments that we identify, but not even them are correctly labeled. So we're trying to use Rockafellian relaxation. In this case, this is just simply an accuracy test. This is the area under the precision recall curve. This is how one would measure accuracy. I guess you would like to see high numbers. And this is on the first axis is how much mislabeling you have. So when you see 0.10, that means that 10% of my 143,000 training data point have been mislabeled, meaning toxic was called not toxic and vice versa. So imagine if we are here, this here is the advantage of using Rockafellian over plain empirical risk minimization. I guess this is 4 or 5%, but for these people, 4 or 5% is a big thing. Of course, we would like to see more, but at least we seem to have a smaller edge in this case of a more realistic, challenging problem. There's much more that can be said. I think much of this talk came from that paper. We'll do is Chen. I said some of you might be interested in infinite dimensional problem. We started talking a little bit about that in this paper, Eugene Feinberg. This thing about composite optimization is mentioned a little bit in that paper. And of course, in our textbook, we discussed this Rockafellian. In fact, that was the first time we introduced this concept of, or the term, not the concept, but the term Rockafellian was introduced in that book. Thank you very much.
Very nice. Are there any questions from the audience in the room or online if you want to either turn on your mic or send something in the chat? Yeah, Rami.
Is the early stopping that you observe, is it true for any Rockafellian that you choose or just for a particular?
We have only computed with this Rockafellian with the 1 norm and the 2 norm. And mostly the 1 norm, it seems to be where it shows up. As I said, this early stopping, we don't have any good theory for why that is happening. So I think that's an open question. But I think you're familiar with lasso regression. In a way, I feel the 1 norm makes me think about lasso regression. And, I think one can make some hand-wavy argument why it might happen in such a setting. But on the record, I'm not sure if I'm willing to say exactly why is a little unclear to me, but that's something to look into. We think it's rather interesting that that somehow we're able to identify this early stopping without a validation test. It sounds like maybe it's a practical advantage. I mean, early stopping is kind of like a heuristic business in the first place. So, but why, I guess, we'll have to discuss that. I'm not sure exactly, but at least for one norm, Rockafellians, it seems to be the case.
Other questions? So maybe you could comment a bit more on what's open in the theory on this last couple of slides. So the algorithm, for example, or
yeah. So open question could be how to solve these Rockafellian problems better. Of course, since anybody can come up with their own Rockafellian, this is an open area. I mean, very broad area. But I'm not asking you to not only optimize your X, but X and U. How can I do that? I think. This relates, of course, to augmented Lagrangian, where one can often have an explicit formula of the U optimization that disappears, and I alluded to that. But you might not want to do that for computation. You should just do optimization over the bigger space. How would we do that? Well, there's a natural alternating direction algorithm. When will it converge and things like that? One can discuss for sure that. And doing this analysis in context of infinite dimensional problems will certainly be something that we just started looking a little bit in that paper. Another open question, I think, is things like rate of convergence. In this setting, I gave you one rate of convergence, the 2/3.
Yeah.
And that is under 2 norm. What other rate of convergence will you have in other situations? And then I just generally, what are good Rockafellians? So I said everybody come up with their own Rockafellian. So I think who knows what is a better one, depending on what you're trying to do, you know, computational advantages and things like that. There's a lot one can try there.
And I guess a follow-up to that would be, so if I look at the last couple of examples where you perturb the probability distribution, it seems like you might get something more robust. In a sense, to just using P nu itself, like you said, what we should.
Exactly.
So how does that relate to distributionally robust optimization?
Yeah, exactly. I didn't talk. We can talk much about that. Of course, there's this little big literature about distributional robust because they're going in a diametrical opposite direction of what we're talking about here. Distribution robust, you're looking at the worst case, of course, inside of some family distributions. What I'm really doing here, right? I'm going looking for the best case. I'm allowing myself to change the probability measure to find what's more favorable to me.
Yeah.
So I'm diametrically opposite distribution robust. But if you think about it, and this goes back, maybe the easy way to explain it to you is that you remember the simple fact from probability theory. If I have a sequence of weakly converging probability measures to a probability measure, but look at their expectations, they might not converge. But which way can you be? Well, is the lim inf is too high. So I'm coming in too high when I look at expectations or weakly converge, respect to weakly converging distribution measure. So I'm too high. So what if I do distribution robust? High becomes even higher. So that takes you even further away. I'm too high. What do I need to do? I need to relax it. And that's what we're doing here. So I need to relax it. Otherwise I cannot come in. And that even is Fatou's lemma. It comes from Fatou's lemma in a way. So in that sense, if you're in a situation where Fatou's lemma is strict, distribution robust would just do it worse. Of course, you know, there's a complication, of course. In general, we have a downward bias. If that changes or the measure is due to sampling, there's different dynamics that might push you down in a way, so we're not in a Fatou's lemma being strict. But if you're in a situation Fatou's lemma is strict, then one needs to relax. And this is that's the underlying mechanism here, why sometimes convert does not, and Rockafellian does convert in those cases.
Very nice. Other questions?
Yeah.
Yeah, one question about what you were just talking about. So basically, let's say you have these wrong labeled numbers, and what you're optimizing for is giving you also the truth about these labels were wrong. But if you would do robust optimization, you would say, what is my optimum in case these labels turn correct at some point, right? And that's like the anti thing that you're doing.
Yes, so let's talk about it in that setting. So if the robust thing in that setting would be, say, I have this example, or have these images. I suppose the probability is 0, but I'm giving them 1 over n.
Maybe tomorrow a 1 is a 0, or one day of the year a 1 is a 0. Then you would have to do robust, but you will find out the truth with your method.
No, well, maybe you say, but try to say it in my own word. It's easier for me to explain. You have currently nominally 1 over n. What is robust doing? It's trying to look at a worst case. So you might know very well that 1 over n might even be increased. It was brought down to 0, but it might even be increased because this is an example that somehow stands out and was really brought up. But that's the wrong direction to bring it up. We should really be knocked out. So what we're doing here, we're saying that let's look at what could be most favorable for us. And we say, okay, this is a kind of like a guy way out there. The best to just simply knock it out.
It probably is wrong.
Exactly, it is probably wrong. So you can see how this can help us with outliers in general, because an outlier, of course, in statistics is one that would be tough for a neural network to fit. And here we have the flexibility to simply ignore it. Of course, this can sometimes get you in the wrong direction, but here you see, I ignored 544. I can go back and say, which one did I ignore? Should I ignore or not? Of course, there's a whole discussion we can have around that, but at least one say, hey, we're going to ignore these things, and things looks better for me, and then we can afterwards do some sort of analysis if this is really what we want to do, but it highlights what seems to be potentially an outlier, at least. And the distribution robust would not do that.
Yeah, if you think about it, the problem where you had the expectation of pi plus ui, right? Distribution robust wouldn't have min over u and x, it would have min over x, but max over u. Yeah. And the u's would be reweightings of the pi's themselves. So like it would actually sort of put all the weight onto some of those lowercase f sub i's that might actually be completely insignificant to begin with, right? And focus all your attention on that. So it's really a fundamentally different.
It's a little different thing.
I think.
Yeah, exactly. And the question is, of course, this is not a remedy for everything, but I think there's certain situations in particularly this outlier regime, mislabeling, all those things, where this can be useful. But even just to enhance stability of a problem, whatever the reason for the instability might be. But maybe it goes against human nature. Human nature will want to be conservative, and we want to. But maybe sometimes that's not the right thing to do. I'm more an optimist.
Yeah.
So.
Okay. Any other questions? Great. Let's thank Johannes again. See you next week for our last meeting of the year.